Hello Thematics, I'm Teacher Kai, and for today's video tutorial we will be taking a deep dive into the fascinating world of number theory with a detailed study on the Euler phi function. So if you're feeling up for an exciting mathematical journey, buckle up. The Euler phi function is a fundamental concept in number theory. It is named after the Swiss mathematician Leonhard Euler, who lived from 1707 to 1783. He made significant contributions to various fields of mathematics including number theory, calculus, graph theory, and mechanics. One of Euler's notable contributions is the development of the Euler's totient function, also known as the Euler phi function. Euler's totient function has several important applications in number theory and cryptography. The function phi n is defined as the count of positive integers less than or equal to n that are co-prime with n, meaning they have no common factors other than 1. Here are some key properties of the Euler phi function. Number 1. Multiplicative property. For any two co-prime positive integers m and n, the Euler phi function satisfies phi m and n is equal to phi m times phi n. This property allows us to calculate the Euler phi function for a composite number by considering its prime factors. Number 2. Prime number property. For any prime number p, phi p is equal to p minus 1. This property indicates that for a prime number, the Euler phi function counts all positive integers less than p that are co-prime to p, which is equal to p minus 1. Number 3. Power of prime property. For any prime number p and positive integer k, phi p to the power of k is equal to p to the power of k minus p to the power of k minus 1. This property helps us calculate the Euler phi function for powers of prime numbers. Number 4. Divisibility property. For any positive integer n, the sum of the Euler phi function values for all divisors of n is equal to n. In other words, if we calculate phi d for each divisor d of n and add them up, the result will be equal to n. These properties provide a foundation for understanding and computing the Euler phi function in various mathematical contexts. By understanding the definition and properties of the Euler phi function, we can explore its applications in solving mathematical problems, designing efficient algorithms, and ensuring the security of cryptographic systems. Now help me welcome Teacher Carlo as he will show you the calculations involving Euler phi function.
Hello everyone, welcome to my YouTube channel. Today we are diving into the fascinating world of number theory, exploring a powerful mathematical tool known as Euler's phi function. So grab your things and let's get started. So what do you mean by Euler's phi function? Euler's phi function is denoted by the symbol of Greek symbol of phi or phi, and it is also a multiplicative function in number theory. But what does that really mean? Let's go deeper in discussing the Euler's phi function. So, Euler's phi function. Based on the definition, Euler's phi function is the number of non-negative integer less than n that are relatively prime to n. So when we say relatively prime, it is the same as co-prime. And when we say co-prime, co-prime is what we call it shares no common factor other than 1. So let's say uh, a and b is an integer that is their common factor is equal to 1. So we have here an example of, let's say our a is 3 and our b is 4. So therefore their common factor is only 1. So that is a relatively prime, or what is coprime. So now in Euler's free function, we want to know how many relatively prime or coprime numbers in integer n. So in Euler's free function, it is denoted by um, phi of n, or in other books they denote this like phi of n. But for me, I will use this notation. So to understand thoroughly the Euler's free function, we have here an example of um, phi of 4. So we wish to find how many coprime of phi function 4. So first is we have to list down the numbers from 1, 2, 3. So we will not include 4 because we are going to find the relatively prime 4. And 4 to 4 is not a relative prime itself. So therefore, the phi of 4 is, we wish to find how many relatively prime. So 1 is coprime to 4. So yes, 1 is coprime to 4. 2 is not a coprime to 4 since they share common factor of 2 and 1. So therefore 2 is not a coprime of 4. And 3 is a coprime of 4. So therefore our phi of 4 is equal to 2. So we have here a properties of Euler's phi function. So there are three properties that I can share to you. First is the phi of p is equal to the p minus 1. So in this property, first property, p is a prime number. Therefore, if we have a prime number, if you're looking to p function of p or a prime number, the only way to do is p minus 1. So what example for this is, if we have a prime number p, or our p is equal to 13, then our p function of our phi of phi 13 is equal to what? P minus 1. So 13 minus 1. Therefore, our p of 13 is equal to 12. So in the second property, the phi of a times b is equal to the phi of a, phi function of a, and phi function of b. So in this property, a and b are relatively prime numbers. So a and b are relatively prime numbers, or they share no common factor other than 1. So one example for this is, um, if we say for phi of a and b is equal to 30. So therefore, our phi is equal to 30. So we wish to find the relative prime, or the prime factor of 30. So one way to find this 30 using the factorial 3, 2 times 15, 3 times 5. So therefore we have 3 prime numbers that are the common factor of 30. So therefore we can write this as p of 2, p function of 3, and p function of 5. So the next step is to use the first property. Using this first, phi of p, phi function of p is equal to p minus 1. Since our phi function of here is now a prime numbers. So therefore, we can write this as phi of 2 is equal to p at 2 minus 1. Then our p of 3 is 3 minus 1. Then 5 minus 1. Therefore, 2 minus 1, 1 times 3 minus 1, 2, and 5 minus 1 is 4. So therefore, our phi of 30 is equal to 8. So therefore, there are 8 relatively prime, that is, there are 8 prime numbers that are relatively prime to 30. So the third property of Euler's phi function is the phi function of p is to the power of a is equal to p raised to the power of a minus 1 times p minus 1. So one way to understand this is we have an example of p of 1000. So this property is useful in finding the relatively prime of a larger number. So before we proceed to the third property, we wish to find the prime factor of 1000. So the only way to find this, you can use Bayesian algorithm, factorial tree, or any uh, methods in finding the prime factor of any number. For me, I will use this division. 2 divide 1000 is 500. 2 divide 500 is 250. And 2 divide 250 is 125. 125 can be divided by 5. We'll get a 25. Divide by 5. We get 5. Divide by 5. We get 1. Therefore, our prime factor of 1000 is 2 to the 3 times 5 to the 3. So now we can apply the third property of Euler's phi function. So therefore, our 2 to the 2 e to the power of 3 is we can use this formula. Now the second thing we need to do is we set 2 to the third times 5 to the third is to write this as p function of 2 to the third using the second property times the p function of 5 to the third. So now we can use the third property of Euler's p function, which is the p function of p function of p raised to the power of a. So p to the a times p minus 1. So our p here is 2. 2 times 3 to the power of our a is 3 plus 1 times p 2 minus 1. Same goes with our p function of 5 raised to the power of 3. Our p is 5 raised to the power of 3. 3 minus 1 times 5 minus 1. Then we do the math. 2 times, 3 minus 1 is 2 times 1. Then 5 raised to the power of 3 minus 1 is 5 to the 2. And 5 minus 1 is 4. This is 4 by the way. 4. 2 raised to the power of 2. 4 times 1, 4. 5 raised to the power of 2, 25 times 4. So we get the final answer of 400. So therefore, our phi of 1000 is equal to 400. So, so that's how we calculate or compute the Euler's P function. First is um, by using the properties of Euler's P function. The first property is the P function of P is equal to P minus 1 if P is a prime number. Then the second one is this P function of A times B is equal to the P function of A and B if A and B are relatively prime. Then the last one is the third property is the P function of P raised to the power of A or any number is equal to P raised to the power of A minus 1 times P minus 1. So the only thing we need to do is to um, use the properties of Euler's P function in order to find the coprime or the relative prime of any number, integer number n. So I hope you learned something from this video, and thank you for watching.
So good day everyone, my name is Justin Ray Giulino. So in this video, we're going to discuss the application and importance of Euler pi functions. Application and importance of Euler pi function. Application of the Euler pi function. The first one is the RSA encryption or Ravish Shamir Idleman. Discover how the Euler pi function plays a pivotal role in the RSA encryption algorithm, ensuring secure communication and data privacy. Next is the Fermat's Little theorem. Learn how the Euler pi function connects to Fermat's Little theorem, a fundamental result in number theory with far-reaching applications. Lastly is the cryptography and cryptanalysis. Unearth the application of the Euler pi function in cryptography and cryptanalysis, unveiling secrets and vulnerabilities hidden within encoded message. And next discussion is all about the importance of Euler pi function. The first one is the number theory. The Euler pi function is a fundamental tool in the number theory, contributing to the study of prime numbers, divisibility, and modular arithmetics. Second is the cryptography security. By enabling the development of secure encryption algorithms, the Euler pi function reinforces the foundation of modern cryptographic systems. The last one is the algorithms and combinatorics. From permutation algorithms to combinatorial design, the Euler pi function form a vital components in various fields of computer science and mathematics. Here are the examples and real-world application of Euler pi function. The first one is the FIFA World Cup schedule. Discovering how the Euler pi function can assist in designing balanced and fair tournament schedules, taking into account team preferences and venue constraints. Second is the public key crypto system. Explore how public key crypto systems like Diffie-Hellman key exchange and El-Gamal encryption rely on the Euler pi function for secure key generation and distribution. And the last one is the Euler's totient theorem. Dives into Euler-Totient theorem, which utilizes the Euler pi function and its application in the field of modular exponentiation and prime number generation. Conclusion and key takeaways. The Euler pi function provides valuable insight into the properties and behavior of numbers enabling complex calculation and cryptographic protocols. Second, its applications span a wide range of fields, from cybersecurity and computer science to number theory and combinatorics. Lastly, understanding the Euler pi function opens door to a new perspectives and problem-solving approaches in both theoretical and practical domains.